Taylor's principle of limit gauges defines that here are the four statements. First one is go gauge should be incorporate as many dimensions as it is convenient and suitable to gauge in operation. No second statement is no gauge should incorporate as many dimensions as it is convenient and suitable to gauge in operation. And here the third one is separate go gauge should be used for each and every dimension. Separate no go gauge should be used for each and every dimension. Here in of these the correct statements are, the first statement is correct, that is go gauge should incorporate as many dimensions as it is convenient and suitable to gauge in operation. And next one is fourth one is the right, that is separate no go gauge should be used for each and every dimension. So the option the C is the right answer. The elbow nozzle assembly as shown in the figure is in horizontal plane. The velocity of jet issuing from the nozzle is, so here this is the inlet of the pipe and this is the outlet of the pipe. Here outlet there is a nozzle connected of diameter 25 mm, and here at the inlet the pipe diameter is 100 mm and it enters with a velocity of 15 meter per second. So here let us say this is a section 1 and this is a section 2. Now just apply a continuity equation between 1 and 2. So continuity equation is nothing but AV is equal to constant, A1 V1 is equal to A2 V2. That is the mass of the flow, mass flow rate is always constant between any two sections in a pipe flow. So here it is an encompassing flow, so that rho is constant, that's why we are taking AV is equal to constant, that is A1 V1 is equal to A2 V2. So here we will have to find out the velocity of the jet issuing from the nozzle. So here V2 is the velocity of the jet, so here A1 by A2 into V1, where A1 is the area of the pipe and A2 is the area of the nozzle at the exit. So here A1 is nothing but pi by 4 d square, that is let's say this 100 square by 25 square into 1.5, which gives a value of 24 meter per second. So in the option the right option is C. C is the right option. In an hydroelectric generating plant there are 5 turbines of 680,000 HP each running at 105 rpm. Under a head of 65 meter, the efficiency of turbine is 91%. A model of the above turbine is tested in a fluid flow rate of 417 liters per second under a head of 4 meter. Find the ratio of the size of the model to prototype. So here first write down the information regarding prototype and model. So in coming to the prototype, there are number of turbines are 5 and a power of 68,000 HP. Let us say the prototype is represented by A, suffix A, and the speed of the prototype turbine is 105 rpm each under a head of 65 meter, and the efficiency of turbine is 91%, so which is equal to 91%. And coming to the model, a model of the above turbine is tested in a fluid flow rate of 470 liters per second. Let us say this is QM, 470 liters per second, and under a head of 4 meters. So this is the given data. Now coming to the solution, we will have to find out the ratio of the size of the model to prototype. So here we will have to find out the ratio of the diameter of the prototype to the model. So for this we can use the specific speeds and specific parameters as well as unit parameters. So from the relation Qn square by h power of 3 by 2 is equal to constant, so we can find out the speed of the model turbine. But for that first we will have to find out the flow rate in prototype turbine in each turbine. So here the flow rate in each turbine is comes from power formula, that is efficiency into WQH, where W is the specific weight of the fluid and Q is the flow rate and H is the head available, and efficiency represents heat represents efficiency. So here PA is equal to, so we know that all the values here PA is equal to 68,000 HP. First convert it it into watts and then substitute all the values. From this we can get QA, that is equal to 87,385 liters per second. So this is the first step. And coming to the from this equation, Qn square by h power of 3 by 2 prototype is equal to Qn square by h power of 3 by 2 model. So here we know the discharge in model turbine as well as prototype turbine, and we know the speed in prototype turbine, and we'll have to find out the speed in model turbine, and we know the heads available in both the types. So that from this equation the speed of the model turbine is equal to 84 rpm. It's nearly 84 rpm. And from the relation dn by root h is equal to constant, we can have dn by root h of prototype is equal to dn by root h of model. So from this equation we can find out dA by dm, that is nm by na root of ha by hm. So it gives a value of 3.22. So this is the ratio of dA by dm, but here we require the ratio of model to prototype, so which gives a value of 1 by 3.22. So in the option, the right option is A. A is the right answer. For laminar flow over flat plate, the local heat transfer coefficient Hx varies as x power of minus 1 by 2, where x is the distance from the leading edge of the plate. The ratio of the average coefficient HA between the leading edge and some location A at x is equal to x on the plate to the local heat transfer coefficient at A is. So here generally the average heat transfer coefficient is given by 1 by x, 0 to x power of minus 1 by 2 dx. So this is the representation of average heat transfer coefficient. Since here we will have to find out the ratio of the average coefficient between the leading edge and some location at A is equal to some location A at x is equal to x. Okay, here average heat transfer coefficient we will have to find out between the leading edge and some location. Let us say take a flat plate and consider any flow between flow, and here leading edge is nothing but the starting point of the flow and trailing edge is nothing but the leaving point of the plate. So here entrance point of the plate is nothing but leading edge. So here the ratio of the average coefficient between the leading edge and some location at x is equal to x. Let us say that from the leading edge to at x is equal to x to the local heat transfer coefficient at this point. So here already we know that the heat transfer coefficient varies as x power of minus 1 by 2. So this is nothing but local heat transfer coefficient, but we will have to find out the average heat transfer coefficient, that is given by HA equal 1 by x, x power of minus 1 by 2. So here 1 by x into, here it is equal to 2x power of 1 by 2 from 0 to x. So here it is equal to 1 by x 2 into x power of 1 by 2, which is equal to 2 into x power of minus 1 by 2. So this is the average heat transfer coefficient, that is 2x power of minus 1 by 2. But we know that the local heat transfer coefficient is equal to x power of minus 1 by 2, that is 2 into hx. So here HA by hx is equal to 2. So this is the ratio of average heat transfer coefficient to the local heat transfer coefficient at x is equal to x. So in the option, the right option is B.